Hey guys, back with another 10-point free response question to do for practice. This one's really good. All the math does not require a calculator, so very representative of what you might see. There is a pretty tough part. Part E is challenging, challenging your memory more than anything else, because it's not something we hit very hard, but it is something we did hit. All right, so let's dive right in. So part A wants us to explain why the diagram on the left is a better representation for bonding in the fulminic acid. Justify your choice based on formal charges. So formal charges, you know those are going to have to come into play, because if you look pretty quickly, you can see everybody's satisfying the octet, right? We got 8 for the carbon, 8 for the nitrogen, 8 for the oxygen, and the same is true with this other molecule too. So everybody's happy octet rule-wise. And if you got a question like this, you would want to make sure you describe the formal charge, right? If it says justify based on formal charges, give the formal charges of everything that's different between the two. So I don't know if you remember formal charges, but it's the number of valence electrons from the periodic table, right? Minus the total number of bonds plus the number of other electrons that are not in bonds. So this carbon here, looking at this guy, this first carbon on the left, it's got 4 bonds. So valence electrons from the periodic table, carbon, where it is on the periodic table, tells you it's got 4 valence electrons. So 4 minus 4 is 0 for that guy. The nitrogen should have 5 based on the periodic table, and it's got 4 bonds on it. So 5 minus 4 is 1. It's a positive 1. And then the oxygen has 6 electrons. So you don't count lone pairs, you count electrons. Remember, with hybridization, you're going to count a lone pair as each thing, but this is not hybridization. We're looking at formal charge. So you count every electron plus every bond. So it's going to be a total of 7 here. 6 electrons that are not in a bond plus 1 bond. That equals 7. And from the periodic table, it's 6. So 6 minus 7, we should have minus 1 on that guy there. Okay, so those aren't too bad. Looking at this guy, we don't have to worry about the hydrogen, but the carbon's a little funny here. I've got 3 bonds plus 2 electrons, so that's 4 minus 5. That puts a minus 1 on the carbon. The nitrogen has 5 minus 4. The nitrogen's the same as it was before. It's got 4 bonds again, so this is also plus 1. And the oxygen this time has 2 bonds plus 4 electrons. That's 6. So 6 from the periodic table minus that 6 that we just added up, and that gives us 0. So the diagram on the left is better. This is definitely a better version. Now you look at the formal charges, and they're really not that different when you total them up. We've got a total of 0. There's only 1 atom with a negative and 1 atom with a positive. As far as that goes, it's not that big a deal, but hopefully you realize formal charge that's negative should always be on the most electronegative atom. So if we're going to have a negative charge in the formal charges, then it needs to be on the most electronegative atom. And in this case, that's oxygen. So 2 points here for this question. 1, assigning the formal charges. That's 1 point. And these should be written out. In the case of your exam coming up, if you have a question like this, you're going to type them in. Carbon's formal charge is 0 on the first one, minus 1 on the second one. Oxygen's formal charge is minus 1 on the first one, 0 on the second one. And then for the second point, you need to say that the molecule on the left is better because the formal charge that's negative is assigned to the most electronegative atom, which is oxygen. So negative, and you would need more words than this, obviously, but on the oxygen. And you would also need the word electronegative because it's more electronegative. Part B, we're using these diagrams, and we're going to see we need to find the total enthalpy of this reaction. So here's my reaction. I'm turning this guy into this guy. And so I'm going to break every one of these bonds. All 3 of those get broken, and I'm going to form all 3 of these because I am just swapping the places of the nitrogen and the carbon. So just make yourself a little table. We're going to break, and we're going to form. And so we're going to break a CH. We're going to break a C triple bonded N. And we're going to break an N single bonded to oxygen. We're going to form an H with an N. we're going to form an N double bonded to a carbon. We're going to form a C double bonded to an oxygen. And so these are all going to be positive values, remember, because you have to put energy in to break bonds. And these are all going to be negative values because you get energy out when you form bonds. So you just go to the table and put these values in. So CH, I'm going to have to put in 413 kilojoules per mole to break that. I'm going to have to put in 891, and I'm going to have to put in 201. Add all those up, and I get 1505. So that's my positive value. Then I'm going to form 391. I'm going to form 615, 745, and I add up all those, and of course they're negative, so negative 1751. Then I just do the math, so 1505 minus 1751 equals, and that's negative 246, and our units are kilojoules per mole in the reaction, right? So an exothermic reaction, I guess it's not asking us anything of that. All it wants to know is what's delta H, and there it is right there. Don't forget your units, don't forget your negative sign. Looking at part C, a student claims that delta S for the reaction is close to 0. Explain why this claim is accurate. Well, your initial response might be to try to do some math to show this, but you don't have delta G. You don't really have any way to calculate delta S. But if you remember, delta S, of course, is entropy, change in entropy. When we get entropy questions, a lot of times all we got to look for is changes in states or changes in the number of particles. And when you go back to this original reaction, which is right here, there are gases on both sides. Their molecules are exactly the same size. There's only one molecule on each side. So we're really not changing anything that's going to affect the entropy. So you need to say something like that this entropy, the claim is accurate because, don't start your answer like that. Two things though, not changing number of molecules or number of particles, and we're not changing the state of matter. So both of those contribute to a very, very small change in entropy. This is worth 1 point. Would you get that point if you only said one of these two things? I don't know. It's a little unclear from their rubric. Maybe. Which is present in higher concentration at 298 K? So we need to look at thermodynamic favorability. So when it says justify your answer in terms of thermodynamic favorability, we're talking about delta G, and the equilibrium constant, we're talking about K. So this was an equilibrium reaction. If you look back up there, you'll see that it's got the little double arrow. So what do we know about delta G? We know that delta H is equal to negative 246. We calculated that, kilojoules per mole. We know that delta S is close to 0. So delta G is equal to delta H minus T delta S. If this is close to 0, that whole thing can be chucked out. So it's pretty close to delta H. So delta G is near negative 246 kilojoules per mole. So it's negative. Negative delta G means spontaneous in the forward direction, right? So that means it's going to shift everything towards the right. So negative delta G means that K is greater than 1, which means we're getting more product. We're going to be more towards the right. So you go back to your original reaction, this guy again, and who's on the right? It's the HNCO. So more HNCO at equilibrium. Now this is 2 points, one for this and one for this, to get this delta G is negative. So the part E here is kind of tough. We've got this graph, we've got some data. We're looking at a decomposition reaction. There's no coefficients, so this looks like a first order reaction based on that, and that's what this is showing you here. There's no exponent on this, so that's first order reaction. But it doesn't ask, how does this equation support the proposed rate law? It asks about the data. And when you look at the data, you can see we've got this kind of exponential decay going on, and it's very clearly a half-life graph. You can even see that at 10 seconds, we're at 50% of what we started with. 10 seconds later, we're 50% of that. 10 seconds later, we're 50% of that. So this is a straight half-life graph. If you didn't figure that out from the data, hopefully when you got to part 2, Roman numeral II, it asks you to calculate K. Now to calculate K, there's a couple of different ways on your equation sheet. Remember that this one right here is first order, but there's also this little guy right here, and we can do half-life. So using the half-life, we can find K. And that brings you back to this first part that tells you, hey, that looks like a half-life decay. That's first order. Remember that half-life equation is only good for first order reactions. So that part I don't expect you really dug out of your memory. Maybe you did. If you did, well done. But we're digging it up now, so time to use it. All you have to say to get this first point is this looks like a half-life decay and half-life is a first order reaction. To get the second point, you just have to solve for that. So the half-life is equal to 0.693 over K. I want to find K, so I just got to put it over here, and so it's going to be K equals 0.693 over the half-life. And if I look at the graph, there's my half-life right there. There's half as much of what I started with, and that's exactly 10 hours. Or you can look at the data table and see that when I have half of what I started with, that's 10 hours, either way. And so 0.693 over 10 equals 0.0693, so no calculator needed. And my units here are going to be hours to the negative first, right? It's 1 over hours because this is hours. And this has no unit on it. So I'm not sure exactly what kind of editor you're going to have available for typing. I expect you will have access to exponents and subscripts just because of the nature of chemistry. But this is your correct answer, and that's worth 1 point. So 1 point for part 1, 1 point for part 2. Last section, part F. Student learns the decomposition reaction is run in a solution of pH 13. Briefly describe an experiment, including the initial conditions that you would change and the data that you would gather. So what is the independent and what is the dependent variables to determine whether the rate of the reaction depends on the concentration of hydroxide. So we need to run this experiment at different concentrations. So you could say at different pH or hydroxide concentration. So we're going to run this at that. And what are you going to collect? You're going to measure the same thing they measured before. It was just the concentration of the urea. That's what you're going to do. And then you're going to use these data to calculate K. Just like we did before. Based on the actual rubric, this is only a 1 point question. And so you have to say that you're going to run it at different, I didn't put different in here, but different pH or hydroxide concentrations. And then you're going to measure the concentration of urea. And that's all you had to say, and you would get the point. All right, so that's all of that one. Guys, you got to keep doing this day to day. Don't put this off. Hang in there. We're almost there. You're going to do great.